Hi, good afternoon, everyone. We'd love to welcome Mr. David Friedman. He's a structural engineer with a lot of experience in the field, and it's an honor to have him with us in our country. Um, he's going to talk about earthquakes and structural engineering practice and project perspectives with 3 case studies. And please refrain, I'm going to also say this in Spanish so it's clear. Please send all your questions through the chat, and in the end, we're going to have a Q&A session where all your questions will be answered. Por favor, manden todas sus preguntas en el chat y al final, que cuando finalice la presentación, entonces el ingeniero procederá a responderle todas sus preguntas. Please enjoy. You may start, Mr. Friedman.
Thank you. Thank you very much. Good morning from San Francisco, California. I know you're all in the afternoon. I'm delighted to be with you today. I would be happier if I was on campus with you. I love making these visiting professional visits and presentations, mostly because I love meeting students and faculty on campus. So I offer a standing outreach invite that I'd love to come visit sometime when travel allows. The reason I love doing these visiting professional programs is because, you know, here I am at the end of my career, and it's fun kind of imparting to students at the beginning of their careers why it is I am so bullish on the profession. And really, there's only a couple of things you really need to know about me. One is I've loved my career. I loved my job, and earthquake engineering has kind of framed and shaped my career because of earthquakes, because of the projects that I've worked on, because my specialty or my interest became the seismic rehabilitation and strengthening of historic structures. I'm glad that there was already an introduction to EERI. I joined EERI really early in my career, and frankly, EERI shaped my career in so many ways. And not only as students do I suggest you get involved, but also after you're in school and when you're in practice, even if you're not really focused on earthquake engineering, I think there's a lot you learn about the world, disaster risk mitigation. And one of the things that's particularly unique about EERI is you get to meet a lot of people in a lot of different disciplines associated with disaster engineering and risk planning. And particularly for me, what was so broadening was meeting social scientists, people who were involved with disaster preparedness and post-disaster recovery. It really is the Learning from Earthquake program that helped shape my career, and one of the reasons that I've loved my career is because I feel like I've been on a continuous learning path, and the education I get constantly from the LFE program is what's so unique. So I'm going to talk to you a little bit about my career, a little bit about my perspective. I will intersperse a little bit of my timeline. I've had 3 jobs in my entire career: 2 years, 3 years, and 40 years. I officially just retired from Farrell Elsesser at the end of 2020. I still am actively involved on the board of directors of the company, and involved with some other for-profit and nonprofit engagements around earthquake engineering, advocacy, and policy. And as I mentioned, earthquakes have shaped my career for a number of different reasons. The timeline, again, now inserts a lot of earthquakes. The highlighted ones in yellow are ones where I participated with a interdisciplinary reconnaissance team. One local, the Loma Prieta one, but then Kobe, Japan, and Wenchuan, China. But the other earthquakes during the course of my career also had a profound effect for a number of reasons. Now, I wasn't alive for the 1906 earthquake in San Francisco, but later on in my career, I found myself doing the seismic retrofit of the replacement building for this building that had been destroyed in the 1906 earthquake. I was still in school in 1971, but the San Fernando Sylmar earthquake was really a game changer in terms of seismic codes. This building shown in the slide is a hospital building. And you can see that this building was really close to collapse. We cannot afford that to happen with our essential services buildings like hospitals. And also you'll see that those columns were only standing because of the rebar in them, because the concrete blew out. And that was, we learned a lot after that, and the codes changed around the principle of ductility and the idea of transverse reinforcement and concrete resisting elements. The 1989 earthquake in San Francisco was actually a very small earthquake. It's kind of the bane of my existence as a practicing engineer, because it was a big earthquake for Santa Cruz, which is 100 miles south of San Francisco, but the ground shaking in San Francisco and the duration of ground motion was very short. So lots and lots of people would say, hey, my building survived the big one. And I went, really? Your building survived 1906? And they said, no, 1989. And it's like, nope, not a big earthquake. Northridge earthquake, Kobe, Japan, I mentioned. This was a game changer earthquake for me because I had up until this point thought about earthquake engineering on the building projects I was doing. And this really exposed me to two things. One is earthquakes are regional disasters. They don't just affect a building at a time. It affects a neighborhood, it affects a community, it affects a whole region. The second thing we learned from this is brute force approach to earthquake engineering does not work. This is a viaduct structure. Those columns were 27 feet in diameter. They just had no transverse reinforcing, no ductility, and they just blew out. Banda Aceh in 2004 really woke the profession up to the hazards of tsunamis. Sure, we knew tsunamis existed in history, but this earthquake and the after fact tsunami really woke us up. The west coast of the US, I don't think started having tsunami warnings. We don't have a huge tsunami risk, but now you go to the beach and you see the tsunami warning signs. Wenchuan, China, I mentioned that I was on the reconnaissance team for this. This really, one of the stories here was earthquake-induced landslides that wiped out entire villages in the rural areas of Wenchuan, China. Haiti, in 2010, this disaster really was a disaster because they measured the amount of damage in terms of 2.5 times the gross national product of the country. And so it's no wonder that it had a hard time recovering. Christchurch, New Zealand, there were 2 earthquakes within 4 months of one another. The second one was actually a lower magnitude, but it happened right below the city of Christchurch, Christchurch, and it had a profound sense of damage to that city that they're still recovering from. Tohoku, Japan, this is another very large magnitude earthquake, also a tsunami. You probably know this. This is the one where they had a failure in a nuclear power plant and a radiation leak from that. The other story behind this earthquake was the strong ground motion lasted 2.5 minutes. It's a very long earthquake, felt a long way away in Tokyo. So structural engineering, this is my favorite definition of structural engineering. Structural engineering is the art of molding materials we do not entirely understand into shapes we cannot precisely analyze so as to withstand forces we cannot really assess in such a way that the community at large has no reason to suspect the extent of our ignorance. Now, I don't mean to really suggest that we're ignorant or we're not bright, but we have to accept that there's a lot of uncertainty in what we do. We don't know when the earthquake is going to happen. We don't know how big it's going to be. We don't know how long it's going to last for. But we're talking to clients who we have to communicate what it is we can and cannot promise. Some of the issues facing engineering today, the codes. You know, as I mentioned, we chase earthquakes because we learn things, and then we change the codes in response. When I first started practicing earthquake engineering, structural engineering, the code provisions for earthquakes was maybe 10 pages long. Now it's 100 pages long, and you know they're better. But still, you've got to think your way through the code because the code is based upon a life safety mandate. So what does that mean? And how do we translate that? It means that we design buildings so people can safely get out of them. It means nothing about their ability to get back in them. We accept damage in buildings. We know that to dissipate the energy of the earthquake, buildings have to move, because that's how they dissipate the energy of the earthquake. So a code complying building is this building. It's the moderate disruption. But a lot of people think, the public generally thinks, that when the building has been engineered by a licensed engineer, that they're getting an earthquake-proof building. They're getting one of these. Well, there's no such thing as earthquake proof. We do have the technology to be able to deliver high performance engineering, but that's not what the code mandates. And that, I would say, a lot of the architects that I have worked with in my career really don't understand that. So it's something we need to communicate to them. The building code is also based upon kind of regular buildings. Really doesn't translate very well for the types of modern architecture that architects want to produce. And our job is, and these buildings are not deformed shapes of buildings. This is the architecture, and this is what, you know, we have to find regular, rational engineering design solutions to. Sustainability, the latter part of my career, has become, you know, kind of a holy grail of what, you know, we're trying to preach. The problem with sustainability was it was more about energy sustainability and kind of missed the whole notion of seismic sustainability. We also, you know, given the fact that there's so much uncertainty, we engineers do get a bad rap where, you know, we spend so much time in technical classes. Maybe we don't have as much experience becoming good writers and good speakers, but it's really important because and it's even critically important for us because we have to communicate complex technical things to generally a lay public or a non-technical audience. So it's part of the stuff we have to work at as we go into practice and we're explaining to people what we're doing. Now, my favorite part is to talk about some of the projects that I've worked on. And so here my timeline highlights some of the projects I mentioned that for the most part, my engineering career was spent on working on seismic retrofits of historic structures. And I'm going to talk to you about two of those projects. One is the base isolation retrofit of San Francisco City Hall, and the other is the seismic safety corrections of the football stadium, American football stadium, that sits on top of an active earthquake fault. The San Francisco City Hall project, as I mentioned, was the early use of base isolation. I'm not sure I could have assumed that you all know what base isolation is, so I'm going to give you a very quick introductory primer on it. So what are base isolators? Base isolators are these little widgets. There's two basic types. The two on top, which are high damping rubber isolators. They were used before as bridge bearings, but we started thinking of them for anti-seismic design. The elastomeric rubber isolators are really a layered birthday cake, if you will, of layers of rubber, steel, vulcanized, kind of baked together. So they act as one monolithic product. There's also the lead core rubber, where a lead core is put in the middle, which has a dampening effect and a restoring effect. The other principal kind of isolator is what we call a friction pendulum, shown below. That's a concave steel surface and a ball bearing rubbing up against it, and it's moving. Its top plate is moving relative to the bottom. The elastomeric isolators are about 24 inches tall. They can be up to 3 feet in diameter. The friction pendulums can range in size from 3 feet square to 6 feet square. There's two basic reasons why we base isolate buildings, why it's the best anti-seismic system that we have in our toolkit. The first reason is inner story drift. So a fixed base building, and a fixed base building is anything other than a base isolated building. It's a braced frame building, a shear wall building. But the way those buildings behave in an earthquake is they move from floor to floor, and we call that inner story drift. That inner story drift creates damage. That damage, again, is what we expect to happen, because that's how the energy of the earthquake is dissipated, how it's resisted. In a base isolated building, most of that horizontal deformation happens in the isolators. And so it means that we get to design the superstructure has far less inner story drift. It almost moves monolithically. So that's one reason why we base isolate buildings. The second reason is what we call the period shift. So this is, maybe you've seen this is an earthquake response spectra. So it's the fundamental period along the x-axis and a lateral or spectral acceleration or lateral force on the vertical axis. Most fixed base buildings are in that lime green zone. And you can see that, these are about half-second period, fundamental period of vibration buildings, and it puts us at the peak of the response spectrum. So it means we have to design the superstructure for like 1.1 G. But with base isolated buildings, you get a period shift, because a fundamental period of vibration of an isolator is between 2.5, and 3 seconds. And so if you read across, instead of designing the building for 1.1 G, we're designing the building for 0.2 G, or like an 80% reduction in lateral forces. So those are the two principal reasons why we like seismic isolation. One of the first projects that we did was the city and county building in Salt Lake City. And after we had finished that, the 1989 earthquake happened, and that's when we started working on San Francisco City Hall. This is a photo of the new San Francisco City Hall, built in 1915 after the previous City Hall was built. It's 2 city blocks. It's 163 feet tall to the top of the lantern on top of the dome. Again, this is the building that was destroyed in 1906. So this is a cross section through the new City Hall, the base isolated scheme for the building. I'm going to talk to you about really the base isolation, which happens all right in here, where we put in a new foundation, slipped in the isolators, and created a new floor. We did have to do a lot of work on putting in concrete shear walls on the light courts that are on symmetrically each side of the rotunda and the drum and dome of the building. We also had to put in a lot of steel bracing and transfer mechanisms to transfer the load down, because this stiffening was still needed because we were trying to protect the brittle dome of the building. You know, if I had another 2 hours, I'd love to tell you all about that part of the project, but I'm going to tell you just about the base isolation. So this is the best part of my presentation, and I'll show this again, but what you're seeing on the left side is a fixed base retrofit of City Hall, and on the right side is the base isolated retrofit. We use this to explain to the client what we were doing. What you're seeing is a real earthquake time history being input into our model. And so I'm going to show this again, because if you keep your eye on the, okay, I have just the left one going. This is the fixed base. Look how much the dome is moving. Look how much the corner pediments and entry pediments are moving. We would have to done a lot more work. And in fact, we would have had to rebuild the dome if we went with a fixed base solution. Now, if you look at the right hand, you'll see it takes a moment for those base isolators to get activated. But if you keep your eye and compare it, look how little the dome is moving. Again, that interstory drift. The pediments aren't moving as much. The corners of the building aren't moving as much. So that's why we use base isolation. And this animation is where we got the client to say, oh, now I understand what you're doing. The real fun and the real trick was, how do you get the isolators into the building? So I have a couple of construction slides that I think you will enjoy seeing, where the first thing we did a complete demolition inside the ground floor, excavated around the existing foundations, put in pretty much a matte foundation system, and you can see the reinforcing steel going in. All of the concrete encasement of the steel columns were chipped away. And then this next photo shows a number of things. It shows what the preparation is for how we would begin to bypass the load. So these are some very stiff outrigger beams. These are actually steel column sections that are clamped on either side of the column. And then there are these spreader beams that go down to these hydraulic jacks on each side. So once we have clamped the column, and we have these gauges on the lower part of the column to see that the because of the stiffness of this armature, that the load is bypassing it, then we can come in and cut the columns off. Once we cut the columns off, we can, and you can see the cut column here, we can go in, chip out the existing foundation, complete the rest of the foundation, put in these base plates for the base isolators, and you can see the little anchor bolt templates that are there. On the left-hand side, you can see the isolators have been brought in. Now, this particular shot is of 2 of the 5 columns that supported that very heavy dome and drum structure. So we actually have 4 isolators under these. So this now shows the isolators in. They're actually locked into place because we did not want these isolators moving until the entire building project was done. And we bring in these very stiff ground floor girders to reattach the column to. And this is part of the new floor system. So everything below this floor is in the isolator plane. And these isolators were designed to move as much as 3 inches laterally. I also want to tell you a little bit about this other unique project, which is the football stadium, the American football stadium that is on the University of California, Berkeley campus. What's unique about this building, what's unique about this project, also a historic building built in 1922, and it was built in 9 months for a cost of $1 million US, is that this building sits on top of the very active Hayward Fault. So this is a map of the faults that exist in San Francisco. The San Andreas Fault is the fault that went off in the 1906 earthquake. The fault that we are more worried about going off is the Hayward Fault, because it's been 150 years since we've had an earthquake on that fault. Faults creep over time. We can tell a little bit about where the faulting is actually occurring. You can also see some of the creeks that are flowing east to west and how they meandered a little bit. That's because of faulting. Here's a closer up geomorphic representation of the fault that runs right through the stadium. And you also see in green what we call this shutter ridge. And look at the way Strawberry Creek, this underground creek, has completely been diverted. And that is because of the shutter ridge and the creep in the fault that has happened over geologic time. We did a lot of trenching to begin to help us understand where the fault was, but we knew in this representation, the fault was pretty much running north-south through the stadium. We knew that the issue was not as much ground shaking. The issue of trying to retrofit a building on top of an active fault is the fault rupture and displacement. Geotechnical engineers gave us a displacement estimates as much as 6 feet horizontally, 1 to 2 feet vertically. That could be the offset. So this is, before we even knew what our solution was going to be, we did a lot of work, kind of how had professors studied fault rupture behavior. Here's a vertical fault rupture after the San Fernando earthquake. What was interesting to us was how there was almost no damage to the building above. The glass didn't even break. Here was a building that there was actually two parallel buildings. The differences between this building and the previous building was this building was pile supported because of the soft soils. And in a way, what we learned here was that it wasn't good to kind of lock our foundation system into the rupturing soil. This was another slide of a professor from UC Berkeley of a rupture in a tree trunk. We think the reason for this was because of, think of it as having a deep foundation system. The root structure of the tree locked it into the rupture, and that's why the tree trunk split vertically. This was one last smaller example of a small but very stiff structure that was on a level mat foundation. That what happened to this structure with the displacement, vertical and lateral displacement, is it simply twisted a little bit and tilted a little bit, and that's it. So that told us something about what our solution was. We were going to carve out and separate the stadium and create these fault rupture blocks. And we would create a seismic joint. Usually, big buildings, we put seismic joints in them, but those seismic joints just go through the superstructure. In this case, we wanted it to go through the foundation as well. We were going to put the fault rupture block on a very thick, rigid mat slab. We would design the fault rupture block as a structure of its own, sitting on top of this, so that in the event of an earthquake, this block would simply rotate or tilt a little bit. But life safety is our mandate, and we felt like this was a life safety solution to this. So we created in red one of these blocks on the north side, one of these blocks on the south side. This is kind of a blow up detail. The geotechnical engineers actually gave us the angles and the probabilities of where the fault was likely going to occur. Nonetheless, we created a block zone. We then did something like 36 parametric studies where we experimented with what if the fault did rupture where they thought it was? This is a case where we said, what if it diffused itself and ruptured in 3 parallel locations? And maybe if they were wrong and it happened outside the zone of our block, what would happen? We did what we call a finite mesh analysis modeling of it. We used a software called Abacus. We actually did a physical model as well. We found that the physical model, and it's actually our peer reviewer and the seismic review committee of professors on campus who suggested that we do a physical model. They said, we asked them, we said, sure, that's a good idea. How would we suggest we do it? And they said, I don't know, you're the engineers of record. You try, you figure it out. So we did. We came up with a kind of a crude physical model, and we just kind of order of magnitude tested it against our analytical models and thought it was, it correlated very well. I'm going to quickly go through one other aspect of the project, because we spent so much time on the fault rupture, we forgot about the West Bowl. And we found that we had a problem because we had this big press box that was 330 feet long. that had a lateral force span of like 200 feet, supported on these concrete core structures. And if you took a cross section, transverse cross section, we had these periodic radial walls, but we still had this triangulated, very stiff structure laterally, and then this structure that's kind of an inverted pendulum. And we found that our solution, because we've retrofitted a lot of non-ductile concrete structures, but this we kept fighting the two elements together. They just wanted to move differently from one another because their stiffnesses were so very different. So we started doing some things like relieving some of the stresses in these raker beams. We tried to put some more ductility in the yielding at the top of these piers. That didn't seem to be enough. We went to the architects for the first time in my career. We said we had the idea of putting an opening in a shear wall, but that was only so that we could ductily reinforce these piers. That still didn't quite get us where we needed to go. And this is one of the things that I've found in my career is sometimes you get lock set in your solution, and sometimes you have to step back. And finally, what we did here is he said, why are we fighting this? Why don't we let the two structures behave independently? So we carved them free from one another. We put a collar around them. We vertically post-tensioned the piers, and then we even introduced hydraulic viscous dampers to help control the differential motion between the two. We did a lot of analysis on this as well. And I very quickly want to show you, some construction photos. These are the radial shear walls. You may not be used to this in your country, but these are what the amount of reinforcing we put in ductily reinforced concrete shear walls in earthquake country. The construction had to be done in a very quick 20 months. Every piece of material had to come in and out of this one arch at the north end of the stadium. And we had to think about that in terms of some of our detailing. This shows the west bowl of the stadium going in. This is the fault rupture block, almost finished construction. Here's the seismic joint, which was very different than the radial grid of the stadium. And this was the first tier of the press box. So this was interesting because this was like a space frame. It had been fabricated at a fabricators in the Sacramento Valley, had been erected there in 5 sections, then unbolted, put on flatbed trucks, trucked into the stadium, and then reassembled to make sure it all still fit. And then they brought in this little yellow crane to erect this crane, which also arrived on like 73 flatbed trucks and had to be assembled there. And the whole purpose of this crane was to lift up these 5 sections of the press box, where we actually detailed it. Normally something that is spanning longitudinally, you design it to do that, but here we designed it in these 5 transverse sections so that it could be picked up and then laced together afterwards, and then they built the second tier on top. We were completed on time and on budget. This is looking up at the stadium from the outside, looking at the press box structure. This is it from the inside. Really one of the more challenging and rewarding projects. Lastly, back to my timeline. At the bottom here, I added a lot of my professional activities and kind of civic and community activities. You know, it was important to me. You know, I think you learn a lot from joining professional associations, but I also it's kind of a social justice guy trapped in an engineer's body, and I got involved in some community and civic organizations. And now at the end of my career, I'm spending a lot of time with some nonprofits, one called Build Change, the other called Geohazards International, that does seismic risk mitigation in the developing world. So you know, I think that's where I like spending my time. I will conclude with saying I think you have great careers ahead of you, and I hope you enjoy your profession as much as I did. And now I've gone a little bit over, but I'd love to answer your questions. Somebody must have some questions.
So we currently don't have any questions in the chat. So you guys can raise your hands and I'll call on to you and you can unmute your microphone and just ask your question.
That'd be great. Okay, I think I see.
Yeah. Okay, so we have one hand raised and we have one question in the chat.
Okay, see the question in the chat. For earthquakes, what is the best type of foundations? You know, it depends on the system. And it certainly depends upon the soil conditions of your site. We also spend a lot of time not only modeling our buildings for earthquakes, but modeling the foundation systems, because there is this thing we called soil structure interaction. You know, it's a fancy buzzword, but it does mean that the foundations affect the behavior and transmit forces into the building. So you know, I think I gave you an example of, at least for the stadium, the best foundation system there was a mat slab, thick, monolithic. You know, most buildings will have more localized spread footings. If you have better soils and good bearing pressures, you're able to use spread footings underneath brace frames and shear walls. You can use strapped footings, you know, but you know that if you have softer soils or buildings where we're dealing with bay mud or something, those buildings always have to be pile supported, you know, and then you have to make sure that you understand the impact on the superstructure design of your lateral force resisting elements. I see another question of how the diagonal reinforcement works. I'm not quite sure by diagonal reinforcement. I think maybe that was in the slide I showed of the transverse shear wall at the stadium. There were these cages of shear reinforcing, which was pretty much okay. Yes, that one. Good. I guess correct. So what that was doing was actually something that wants to behave in shear, but shear failure is much more catastrophic catastrophic than flexural failure. We like flexural failures because they're more robust. So those diagonal cages of reinforcing were trying to provide both shear and flexural reinforcing in those link beams. So it's a very good question. I could probably spend an hour telling you about the design of ductile shear walls, but that's basically what those diagonal reinforcing is trying to do. Then what is a seismic joint? Okay, that's a very good question. What a seismic joint is basically trying to create, if you have a building that is very long, you get to a point where you really need to break it up into sections. And so you give yourself you design a joint between buildings. Normally a seismic joint between elements of a building is maybe 2, 3, 4 inches. In the case of the seismic joint at the stadium, that was a different beast, and those were 12 inches. The other reason that you have seismic joints may be separating different buildings, like let's say you're designing a new building sandwiched between 2 adjacent buildings. You want a seismic joint there because you don't know about the design of the building next door. It may be an older building, it may be moving a lot. One of the things that we don't like happening is buildings, what we call pounding together, so that as the earthquake is happening, if it's moving too much across a seismic joint, or in some cases, like in San Francisco, there are buildings where there's no joint at all. You know, they're just, one is built up against the other. And we learn from earthquakes of how buildings can pound together and create a lot of damage. So that's why we insert seismic joints. Sometimes we even, just if a building is very long, we have to put in expansion joints just because of the thermal expansion of the size of the building. Hope that helps. Okay, here's a question. How did you guarantee the stability of an existing structure when you are intervening the foundation during retrofit? I actually took slides out that addressed that issue. Because of the nature of the projects that I've worked on in my career, sometimes the construction of the retrofit happens over 2.5 years, a long period of time. Normally, the stability of the structure during construction is the responsibility of the contractor. It's what we call means and methods of construction. But early on in that San Francisco City Hall project, we became concerned about, well, what if during 2.5 years there was even a mild earthquake, and that we were taking out some of the brick shear wall and terracotta shear walls that existed there? We needed to put into some temporary bracing. We weren't necessarily making the building stronger, but we were trying to maintain the strength that it had at the time that we took out that stuff. We went to the city and explained that if we left it to the contractor, we might get just little flimsy rod bracing. So we convinced them to allow us to design more hefty structural steel bracing system, temporary bracing, so that at least we weren't weakening the building further during the course of construction. So yes, you do have to think about this during longer periods. What I didn't show you in the Memorial Stadium project, where we had demoed the inside, the entire inside of the stadium, we had to put temporary bracing for the perimeter historic wall so that we could do the demolition on the inside of the building. Here's a question about great definition of structural engineering. In fact, that's the same definition that I told my students. Good, I'm glad. How was the process of choosing what type of isolators to use? Do you use a specific type of isolator depending upon the load that a column is carrying? Really good question. So consider when we were doing San Francisco City Hall. Public sector building had to be publicly bid out to contractors, and that included all materials. And so we had to design the building without a preference for what type of isolator it is. So we wrote what's called a performance specification. So it had parameters for what sort of dynamic properties and deformation properties they had to meet. And so we had both elastomeric bearing elastomeric isolators as well as friction pendulum, and we had maybe 3 different vendors of the elastomeric. At the time, there was only one friction pendulum vendor, and they were selected based upon lowest bid, you know. And so, you know, did we have a preference? You know, maybe somewhat at the time. You know, today we have been involved with some, you know, private sector based isolated buildings, and sometimes the vendor has convinced the client to use their elastomeric isolator or their friction pendulum isolator. So we stay a little bit agnostic on the topic of preference. I do lean a little bit towards the elastomeric one because of their ability to resist net uplift. We did one project where it was a private sector project that was already selected the friction pendulum, and the friction pendulum does not resist net uplift. And the geometry of the building actually induced quite a significant net uplift, and we had to design our own uplift restraint mechanism for that project. What was the hardest obstacle that you had to face to become a structural engineer? Oh, you know, I mentioned at the beginning of my timeline that that I only had 3 jobs in my entire career. My first job, and I was coming out of school, and I wasn't really quite sure exactly what I wanted to do, and I made a decision that maybe I should go to work for a large construction engineering firm, because it might give me the broadest perspective on what I might want to do. I even thought I might want to go into general contracting. So I went to work for Bechtel Corporation, very large international construction engineering firm. I was just happy to have the job, and I think I was a little naive because I didn't ask a lot of the questions I should have had asked, and I actually found myself with the wrong employer for me, and the reason for that is that notion that I was going to get a broad range of exposure and experience. And I didn't. I was working on projects where I was checking calculations and I had no growth ahead of me. And so I think that until I had my second job with a small consulting engineering firm, and it was actually my wife and I was newly married. We had moved to Boston, and the firm I went to work for was a lot more impressed with my Bechtel experience than I was. But they really restored my faith in that I liked consulting structural engineering. Then I came back to San Francisco, and my father was a practicing architect in San Francisco, and I asked him who are the good structural engineering firms, and I was interested in earthquakes, and I wasn't going to find that in Boston, and that was certainly true here. The last firm that I interviewed with was Farrell Elsesser Engineers, and I interviewed with Eric Elsesser, and he said, "I wish I could give you an offer, but my partner Nick Farrell isn't here, and he's actually in Algeria on an EERI post-earthquake reconnaissance trip." And so maybe it wasn't the obstacle that I had to face, but the aha moment for me was that moment when he said he's doing this post-earthquake reconnaissance trip with EERI. It was like, oh my God, how cool does that sound? That sounds like the learning curve I want to be on. So I think the biggest hurdle, all of you face really is, find the place that's the right right place for you, that's the right cultural fit for you, and the place where they're going to invest in you and your learning curve, and just be ready to learn. I think that's what you have to look forward to. I know we're running long, but I'm happy to continue answering questions.
We have one hand raised.
Okay.
Dr. Jan Guzman.
Okay.
Hi, David. Thank you for joining us on your presentation. This is a really good comment what you made about finding a place where you think the learning curve is going to be valuable for your professional development. This is kind of like a full circle moment for me a little bit, because we actually met back in 2013 when I was a chapter officer at the University of Nevada, Reno. I was a grad student then, and that's actually, my experience in the States led me to start this student chapter at UNIVE. And this is now like the second chapter in the country. So I'm very proud of the work these students are doing.
Thank you for doing that. Thank you for doing that. That's fantastic.
Yeah. These students, they face many challenges in their field, and in a place or a country where it still isn't necessarily understood the importance of earthquake risk mitigation.
Right.
And even just like the importance of the role civil engineers play in society in general. you mentioned a little bit about communication skills at the beginning of your presentation. That was actually one of my challenges when I returned back here to the Dominican Republic, that I found was, communicating effectively or communicating to students how important this is. And I think earthquake engineering in general is, like you say, is a very cool field, and it's a great way to showcase what civil engineers can do. So I have another question, but first, if you have any advice on to give them on how to effectively communicate to the general public and other professionals how important the work of civil engineers is.
I spend a lot of time with a lot of civil and environmental engineering departments throughout the U.S. and throughout the world. And honestly, I believe that civil engineering is going to solve a lot of the world's problems and most significant problems, and my focus has been on earthquake engineering, but we all know there are a lot of other natural hazards that are out there, and even that have been exposed to through EERI and other professional organizations. And I do think that, again, one of the reasons why I got involved in professional membership organizations and even some, other social justice organizations is, people working on solving some of the world's great problems, and that can be fresh drinking water, and that can be, look at what we're living under pandemic, conditions. And I sat through a lecture earlier this week by Lord Norman Foster, who's one of the great architects of the world, and he was talking about how talking to engineers about how our cities are going to change remarkably. I think our cities, our workplaces, our schools are there's not going to be a return to normal following this pandemic, and I do think that a lot of the world's challenges and the country challenges are going to be civil engineering challenges, and we're going to be part of the solution to a lot of those. And I think you have a bright future ahead of you, because you have some really interesting challenges that you're going to have to help solve, and the buzzwords of sustainability and resilience are not just buzzwords, they're real things, and how we create our communities so that they are more sustainable, so that they are more resilient after a natural disaster. So, I think you've heard it a number of times from me today. I'm just really, really bullish on our profession, and yeah. I really have enjoyed the learning curve, and that's what's always kept me going. I think my Bechtel experience, where I sat every day watching the clock, as everybody else did. At 5 o'clock you left the office. In the 40 years I was with Farrell Elsesser, I looked at my watch and said, "Oh my God, where did the day go?" Yeah. Because we just didn't get enough done. So I think that's a testament to, I must have found the right career for me. And I feel lucky. I feel lucky that I found something so rewarding.
Thank you. The other question that I have is, we're in a country that is seismically active. We still don't understand fully our own seismic hazards because, well, let's say the current seismic code is 2011, and before that it was like 30 something years. before the update. So
Right.
we don't know necessarily how our current construction will perform during a large earthquake. Um, we haven't experienced fully the impact of a large magnitude earthquake, aside from sharing the island with Haiti and the big earthquake they had back in 2010, I believe. And so, just if you can talk a little bit more about those experiences you had, or what can structural engineers do right after an earthquake event? How can they help, or how can these students get involved in mitigation or anything related to um, reconnaissance?
Right. So I mean, again, this is where our profession is challenging. Because I mean, you mentioned that in your country, um, that maybe um, the mapping of faulting isn't so well known,
Mhm.
and the risk parameters aren't so well known, and maybe not even kind of what sort of predicted ground motions
Mhm.
we know. Most of the time, uh, people will say, what magnitude of earthquake is this building designed for? Well, we don't really design to a Richter magnitude. We design to, what sort of ground shaking, the seismologists give us at the site. But it's, it goes to that definition of structural engineering, which applies so much to earthquake engineering, of, how much we don't know. It should be no consolation to anyone that sometimes we get um, earthquakes happening on that which we thought to be dormant faults. The earthquake that happened in Haiti, there are faults that run through Haiti. It's mostly in the mountains. The earthquake that happened was thought to be on a fault that was dormant. So there's a limitation to how much
Right.
we know. And so, kind of, again, it goes back. I mean, one of the difficulties I've had and challenges I've had in my career, particularly starting with base isolation projects, high performance structural engineering, I got the label, and the firm got a label, of being very conservative art engineers, and that we over design things. There's no such thing as over designing a building for earthquakes. We have safety factors, but there's so much unknown, and that's where I keep coming back to say, okay, I can design a building to code. I can design a building that's life safe. In fact, that's all I can promise you. You'll safely get out of the building. But do you understand that as an owner? Do you understand? And I have lots and lots of photographs of buildings that you and I would not be happy being the designers of after an earthquake, kind of with shear cracks that you can stick your whole arm through, but it's a code conforming building. And if I show them that picture and I say, I can design that for you and I can meet your budget on that, is that acceptable to you? And they often say, no, that's not what we want. So that's where the communication issue of even understanding what limitations of things that we can promise delivering. When someone says, I think that your mandate is to deliver an earthquake-proof building, that's where I quickly say there is no such thing. So I've given you a very long-winded answer. It's a tough one, and it's a conundrum for our profession. But this is part of the challenge that has to be communicated.
I agree. Thank you. Thank you for your time.
Sure. All right. Well, I thank you all. I've gone way over time, but I appreciate your questions, and I really do look forward to a time where I can come meet you on your campus. So would love to meet all of you.
Thank you for your time. I guess we have one more question.
Sure.
Actually, we have two more questions. Do you have time for them?
I do. I'm fine.
Okay, so we have Biandri asked, can you explain how was the construction process of placing the collar and then the viscous damper on the structure?
Okay, so the reason we put the collar in, so that was when we had made the decision to separate the stadium bowl from that inverted pendulum of those concrete cores supporting the press box. So we wanted them to be to move separately. We created a joint. If I'm not mistaken, it was about a 3-inch joint. We put the collar was actually was a cover plate more than anything, just so that someone didn't trip over that 2 or 3 inch gap. We really didn't want to provide a restraint. So by calling it a collar, sometimes we use collars to kind of control motion. That really, it's kind of in a way a misnomer. But we put in the damper, to make sure that the differential motion, because we could get the two structures moving out of phase from one another. One could be moving in one direction and the other in the other direction. So we created there was the potential that there could have been more than an inch and a half movement in each direction. So you multiply that times 2. We could have exceeded the joint that we put in. So we really wanted the dampers to help make sure that we were never going to exceed that seismic joint, and that the two structures would behave independently. So good catch on the word collar, because it really wasn't a collar. And we do, like, even in the fault ruptured joint, where the joint was 3 inches, or the case of a base isolated building where the movement is 30 inches or even 3 feet, we have these cover plates. And the cover plates are so that people don't fall into a hole. But in the event of the earthquake, those cover plates don't become binding elements. They actually break apart, so they don't restrict the building. After the earthquake, they'll have to be put back in. Was there another question?
Yes, sorry. What are some of the challenges you think this generation of engineers will have to face in their lifetime?
I mean, I think I think the world in which we live in post-pandemic will be totally different. I think at least the paradigm shift that we had because of COVID is going to be one thing in the U.S. I think one of the other kind of game-changing things that happened was the racial justice issues in the United States. Things have profoundly changed in this country. I guess I probably shouldn't get into politics too much, but I'm happy it's a new presidential administration in this country. But I can tell you what's happened within Farrell Elsesser and within the structural engineering community is much more attention to DEI, diversity, equity, and inclusion. I'm very proud of Farrell Elsesser. We are now over 50% women engineers. We could probably do a better job of minority engineers. We're making a committed sense of that. I just think, in terms of, I'm maybe skewing the question to where I wanted to go, because I do think there are real engineering challenges around sustainability and resilience. But I also think that there is a wonderful new world about being responsive to the need for diversity, equity, and inclusion, and I think I find that the engineers in the firm are dealing with these issues. They're dealing with work-life balance issues, and we all work to live. We don't live to work. And so, those are some of the human challenges, you will do as you're growing in your career. I think it's actually quite good to be, in with people who are sensitive to the challenges that the world is facing. I think one of the things that's fun about civil engineering right now is that never more so when we work on building design, we're not just working in our own silo. We're working with architects, we're working with mechanical and plumbing engineers, and dealing with things like sustainability, like how can we, in our concrete mix designs, use more high volume fly ash content so that we're not using as much Portland cement, because Portland cement is a notorious carbon producer. So, those are the kinds of things that you'll be facing and involved with as your careers go on.
I guess we have one more question, and then that's the last question for today then.
Okay.
And then we're gonna have Biandy Cabrera. She's gonna make the closing remarks for today's lecture.
Okay.
So the last question, it says, we know that the higher the story, the larger the amplitude. So with that in mind, up to what scale of Richter can a building with a base isolator stand? So
I would answer this not in terms of Richter magnitude or ground shaking, because honestly, base isolation has so much reserve capacity in it. There really isn't a better seismic system than base isolator, but there are limitations on base isolator. Not every building can be base isolated, and the restriction is in the question. It's how high. So if you remember that response spectrum and the period shift, that the fundamental period of vibration is about 2.5 to 3.5 seconds. Fixed base buildings, I said were in the 0.5 second to 1 second range. But as you begin to consider that, that for each story of a building, rule of thumb, it's 1/10 of a second for its fundamental period of vibration. So what you don't want is a building whose fundamental period of vibration is resonant with harmonic. You're probably familiar with harmonic resonance. You don't want a 2.5 second building with a 2.5 second base isolator. So I think that the height limitation of a base isolated building, assuming it's about 3 meters per floor, would be consider it to be a 15 to 20 story building. I think beyond that, I'm not sure isolator is a suitable construction. That's why, most of the high rises in San Francisco, and high seismic activity are usually dual systems with ductile concrete cores and perimeter moment frames. But so that's the way. It wouldn't be a Richter magnitude limitation. It would just be a height limitation based upon fundamental period of vibration.
Thank you so much. Now, Leandri.
Yes, let me put the camera. I don't know if you can see me.
I can't yet.
Oh my God. So my computer is busted.
That's all right.
But okay. So on behalf of the EERI student chapter at UNIVE, I would like to thank you, Mr. Friedman, for your time, this wonderful lecture. It definitely exceeded our expectations. I'm sure everyone is delighted of how it all went. And I hope you enjoyed this time with us. In the same manner, I would like to thank everyone who assisted this lecture. And thank you for your attention. Don't forget to join our student chapter for more webinars, lectures. Follow us on Instagram, EERI_UNIVE, UNIVE, to stay tuned for all the activities we will have at UNIVE. So with nothing else to say, thank you again, Mr. Friedman. I hope we can see each other face to face next year.
Yes, I hope when travel permits, then I would love to find my way onto your campus. I'd love to meet you all.
Yes, hopefully.
Okay, all right. Thanks very much. Thanks for your time.
Thank you.
Thank you.
Thank you very much. And thanks for your questions.